Good morning, everybody. All right. Thank you, Matthew. Thank you, Kimberly, Ronald, Brandon. Thank you. Thank you. I, it helped me to understand that you are getting my voice. You are hearing me. Thanks for your response. Anyway, today I want to go over the test problems, test number 2. And after that, I will cover section 16.4, which is an extremely important section, by the way. It's application of residue theorem, right? Now, here are the problems. And by the way, um, I am a little disappointed of the result of this test, but can't help it. I cannot learn for you. You got to try your best to understand the material, and I'm just here to help. All right. Uh, the first problem is this: we are integrating this function dz, and remember, in complex, always we are integrating over a curve. All right. In this case, that curve is a straight line from -1, which is here, to 1 plus I. So this is the curve C over which we are integrating. Well, of course, we need to parameterize this. Equation of this line that passes through this point and that point is right here. Just going to college algebra, you can write the equation of the line. Now, as soon as you have equation of the line, you can say, okay, look, if x is t, y will be t over 2 plus 1 over 2. Or z of t, well, we usually write equation of the curve in complex in this fashion. This is x, I, y. Now, remember, x is t and y is this. So you replace these in the integrand. And then dz. What is dz? If z is it will be derivative with respect to t times dt, all right? So here we go. So you replace x by t, y by this, and here is dz. The integration goes from -1 to 1 because when t is going from -1 to 1, we will cover all of this curve. Then it is just a matter of integrating this. This is the constant. We can pull it out. And then just integrate this one. Integral of 2t with respect to t is t squared. Integral of this one is right here. When t goes from -1 to 1, you evaluate, all right? And this is what you get. That's it. That's problem number 1. And this technique happens whenever the function is not analytic, you can't find its antiderivative and those type of stuff, all right? You parameterize the curve and then integrate in this fashion. That is number 1. Here is number 2. Number 2, You want to integrate this function, okay? This function looks pretty nasty over this curve. The curve starts from here, goes all the way along the circle up to here, then all the way from a straight line going to this point. But before rushing to solving the problem or parameterizing all those things, you got to think about it a little bit. The function that we are integrating, this integrand, is nothing but z squared, right? Z squared. X plus I y squared is this one. So this integral over that curve is the same as this one. And as soon as you have an analytic function or a function that has antiderivative, the value of the integral doesn't depend on the curve, is independent of the curve. It's just antiderivative. It's like calculus 1. All right? It's just like calculus 1. You take antiderivative from -1 to that point. And here are the points. -1 to this point, which is 2 plus I. Okay? So when you have antiderivative, the integral doesn't depend on the curve. It just depends on the initial point and the last point. That's simple. And here is the answer. That's simple. So if you learn the theory, if you learn the material in the book, you don't go wrong way. You don't go and take wrong approach. With that wrong approach, not only you are wasting a lot of time, but also there are awful, possibility of making a lot of mistakes. All right, good. Here is number 3. Number 3, number 3 is about integration. And the main idea, the main topic of our course is integration. We integrate always over a curve. Now, we are integrating over this unit circle. And the bad points or singularity, e to the z is fine, can never be 0, right? Denominator. The zeros of denominator are the singularities. E to the z can never be 0. This one can be 0, of course, and that is at these points. But both of these are outside this unit circle. So by Cauchy theorem, the integral is 0. Done. Number 2, always we look at z minus a number, right? So in order to create z minus a number, you factor this 3 out. If I take this 3 out, factor it, numerator is right here, denominator will be z minus this number. Well, in this case, when we are integrating over a unit circle, 2/3 is inside. So 2/3 is inside. If this number was outside, the result would be 0, but it is inside. That's when you use Cauchy's integral formula. So it will be 2 pi I times this, then f, which is this part, the good part of the function, evaluated at this 2/3. Okay? And this is the answer. Part C. The singularity is 1. Z equal 1. And we have, well, we have a square in denominator, so we better use that Cauchy's integral formula for derivative. So it will be 2 pi I f prime at that singularity, and f is sine of pi c. Okay? F prime will be pi cosine of pi c. And here we go. Finally, part D of this problem, you see, again, we are always concerned about singularities. And what are singularities? The zeros of denominator. Can this denominator be 0? Of course it can. And that is when e to the z equals 1. And these are the infinitely many times e to the z can be 1. However, we are integrating over this circle of radius 2, centered at 2, and 2 pi I is outside. Negative 2 pi I is outside. So all of these guys are outside. As a result, since we don't have any singularity inside this circle, the integration is 0. That's it. Okay? Any comment, any questions so far? This problem number 3, because there were 4 parts, it had 20 points and 20 easy points. And I'm sorry that a lot of you couldn't get that 20 easy points. Okay, number 4. Oh, look at this. By just looking at that series, you should recognize that it is a geometric series. Remember geometric series? Geometric series look like these. Q to the n goes from 0 or could go from 1 or a number, but in this case, it is going from 0 to infinity. Geometric series. It converges if and only if absolute value of Q or modulus of Q be less than 1. Okay? And if it converges, if modulus of Q is less than 1, it will converge to 1 minus Q. Well, for this one, Q is this fraction. Modulus of Q is square root of 10 over the square root of 5, which is bigger than 1. So this happens if and only if Q be less than 1. Otherwise, it diverges. All right. So divergence, very easy. The next one, part B, also is a geometric series. This geometric series, the difference is modulus of that ratio is less than 1. So the series converges. But of course, you got to know, converges to what? I already told you, converges to this. So a lot of you missed to find the sum of the series. So here is the Q, and of course, when you go ahead and simplify, here is the answer, right? Converges to 5 plus I divided by 2. Okay? Any comment, any question? Okay, number 5. Number 5 was about this finding the radius of convergency. Of course, in these cases, we use the generalized ratio test. If you call that one an plus 1 over an, you form this one, you simplify, you get this. So this series converges whenever this is less than 1. And this being less than 1 means modulus of this should be less than the square root of 3. So this is radius of convergency, right? This is radius of convergence. The next part, same thing. You want to find the radius of convergency of this power series. Use generalized ratio test, simplify. A lot of you had difficulty simplifying or even finding an plus 1. I can help you. If you don't know your college algebra, I'm sorry. I cannot teach you college algebra here. This is complex analysis. Prerequisite for this one is, gosh, not only college algebra, but calculus 1, 2, 3. Anyways, this series converges whenever this guy is less than 1. And this guy less than 1, of course, you want to isolate z, means this, and then you take third root. That's it. Z has to be less than this number, and that number is radius of convergence. Okay? That number is radius of convergence. Now comes number 6. It's about Taylor series. And specifically, it says write Taylor series about 2i, which means center or z naught has to be 2i. In other words, this is telling you that we want the function, the Taylor series, in powers of z minus 2i or z minus z naught is z minus 2i. So we want to expand this in powers of z minus 2i. Well, this part we don't have any problem because it is already in the form of z minus 2i. The main problem is right here, e to the 3z. But e to the 3z, if we want to write it in power series or Taylor series z minus 2i, in the exponent, I am adding 2i and subtracting 2i. So this is e to the 6i times e to the 3 times z minus 2i. And we know e to the anything, e to the w, we know expansion of that. And in this case, here is e to the 6i, and expansion of this guy will be this to the n divided by n factorial. Okay, so this is just e to the 3z, writing in powers of z minus 2i. Now you multiply by z minus 2i to the 4th, you get f of z. So z minus 2i to the 4th goes inside. All right. So here is the Taylor series of this function about 2i. Now, the second part of this problem is pretty interesting. First, we want to write the Taylor series, and then we want to find the 15th derivative of this function or this function evaluated at 2i. Okay, we used a shortcut and we found Taylor series. On the other hand, theoretically, Taylor series of a function at 2i looks like this. Okay, and remember, the Taylor series or Maclaurin series or Laurent series, those series are unique no matter how you find them. So two different approach. Shortcut gave me this, and here is theoretically we know that this is it. So these two should be the same, be equal. All right, when they are equal, the powers of z minus 2i in both cases, the coefficient should be the same. In this case, the coefficient of this z minus 2i to the n plus 4 is this when you replace k n plus 4. In this case, it is this constant times this. Okay? So using shortcut and using the theory, we know that we have this equation for any n. Oh, well, I asked about the 15th derivative. So n is 11. Replace n by 11. So the 15th derivative valued at 2i, here is 15 factorial. You multiply both sides by 15 factorial and simplify. This is what you get. So this is the 15th derivative evaluated at, in general, that's n plus 4, but this is it. Any comment? Any question? All right. That was problem number 6. And now here comes problem number 7, which is about uh, using Laurent series. Okay, Laurent series. In powers of z. This, you got to pay attention to this. In powers of z. For example, if I factor z squared, oh, that's already the portion that is in powers of z. I don't need to mess up with that. But anyways, there are, of course, any math problem, you can have different approaches, different solutions. But in this case, I noticed that some of you, or most of you, try to use partial fraction. Here is the result of partial fraction. I am not going to mess up with this one and this one because they are already in powers of z. I only need to express this in powers of z when modulus of z is less than 1. All right. I factored, could put z denominator 1 minus c because it is the, now, this geometric series, and we know that here is the same thing. And for this one, we have -3 times z to the n, sum of z to the n. That's it. Okay, that's it. If this is called, well, the analytic portion and this principal portion, of course, and the advantage of writing it in that fashion is that right away we know what is the residue of this function at 0. Residue is -3. Okay. Oh, please, if you have any question, just interrupt me, because as I said, I'm a little bit disappointed of the result of this test, and just going through the solution of the test should be another learning experience for you. Here comes problem number 8, which is again about Laurent series. We want to write it in powers of z plus 1. Oh, look. When you want to write in powers of z plus 1, you then mess up with this part because it is already in z plus 1 format. Okay. Well, again, a lot of you try to use partial fraction, and that's why I follow the same. Maybe you learn this way better. So this is the partial fraction. We don't mess up with this because it is already in powers of z plus 1. We need to make this in powers of z plus 1. Oh, look, z plus 1. Of course. Well, how do we create z plus 1 in denominator? Oh, you add 1, subtract 1. Okay. This is this one. Now, this is 2/3. I added 1 and subtracted 1. Okay. Oh, we want in this area, that means z plus 1 over 3 will be less than 1. So why not? Let's factor 3 and actually -3. This is what you get. And now modulus of this is less than 1, it's geometric series. Geometric series. That's it. So, okay. This is the analytic part. This is the essential part. And of course, if you just, in case you wanted to find residue is 1/3. But that was not in the question, though. I am giving you an extra information. Number 9 is about finding the residue at given singularity. Okay. Oh, this is pretty obvious. In numerator, you have a polynomial. In denominator, Z4. So if you write it in this fashion, this divided by this divided by this one, 7 divided by, okay. If you write it in this fashion, that is its Laurent series, centered at 0. So residue here will be coefficient of 1 over z. We don't have 1 over z. The coefficient of 1 over z is 0. That's it. Okay? That's part A. That's I mean, very, very simple way of looking at it. Some of you said, all right, this is a pole of order 4, so you multiply it by whatever z to the 4 and then try to take third derivative. Of course, third derivative of the numerator is 0 because it's a quadratic. Third derivative will be 0. Sure. So if you solved it that way, perfectly fine. You got your credit for it. Here is another one. Well, the singularity of denominator are zeros of denominator, of course, and this is z 1 make denominator 0, but it is a simple pole, right? It's a simple pole. It is not z minus 1 squared, a quantity squared. It is a simple pole. And when you have simple pole, you can use that 2a or 2b. And here, using 2b, so it will be numerator divided by derivative of denominator, evaluated at 1. That's what you get. Okay? Part C. Oh, by the way, this problem had 15 points. Each part has 5 points. Well, again, singularities of this function are zeros of denominator. And zeros of denominator, when z squared is -1, that means zeros of denominators are plus minus the square root of -1, which is I. But we want just residue at I, not negative I. In this case, I is a pole of order 2, okay? It's a pole of order 2. So in order to find the residue, you multiply by z minus I, squared. And then take derivative. It will be right here. Derivative of this guy, quotient rule, and then evaluate at z equal I. And when you evaluate at z equal I, this is what you get. -1/2. All right? -1/2. Any comment? Any question? All right. And finally, the last problem is about using residue theorem and integrating this guy over this big circle. Okay? But using Cauchy theorem, of course, I mean, you don't have to explain this, but I am just explaining to make sure that you understand the underlying logic. So there are two singularities, this one and this one, and both of them are inside. So Cauchy's integral theorem, Cauchy's theorem says integration over the outer boundary is the same as integration over C1 plus integration over C2. Okay? Now, what is integration over C1? When you want to integrate over C1, of course, since there is only one singularity right there, it will be 2 pi I residue at this point. And integration in this one will be 2 pi I residue at this one. All right. As I said, you didn't have to explain this portion. I am doing it to make sure that you understand the underlying logic. So here is all you had to say. But both these singularities, -1 and 2, both of them are simple poles. And you can use either the technique 2A or 2B that I taught you. So I'm using 2B, which is numerator divided by derivative of denominator, evaluated at those 2 points, okay? So here are singularities, 1/3 and 2/3. You will get 2 pi I, okay? That's it. Those are the solutions of the test problem. I really expect you to at least do it for yourself after this learning experience, after we went through the solutions. Go ahead and do it for yourself one more time, and that will help you to learn the topic better. Okay, so next thing that I would like to do is talk about applications of residue theorem. For 9C, you had a formula for finding, here is 9C. Del Dodson is asking about this 9C. It is not a simple pole. It's a pole of order 2. In general, If it is pole of order n, you multiply by z minus z naught to the n and take n minus 1's derivative. All right, that's how it works. You have a formula. You have a formula for finding residues. Then it is not a simple pole. In this case, it is a pole of order 2. So we multiply by z minus I. That is the singularity that we want to work with. If you multiply by this, denominator here is z minus I times z plus I. So z minus I cancels. You get this. We need derivative of this. All right, to compute the residue, you multiply, because it is a pole of order 2, you multiply by this and you differentiate this guy, which is this one. Derivative of this one. After finding derivative, you evaluate at that singularity, which is I, and this is what we get. All right. So, yeah, for simple poles, it's easy. We have 3 different ways, but for pole of order 2 and higher, you have a formula that you need to use that formula. And this is how we do it for pole of order 2. I could have given you pole of order 3, and then you had to multiply by z minus I to the third, and whatever, then you had to find the second derivative, first derivative and the second derivative. All right, but I made it easy. I just gave you a pole of order 2. Okay. So today I want to give you a bunch, at least, if time allows, an application of a residue theorem. Okay, here. Application of there are a bunch of it, but today I will talk about one of them. And that is when you are dealing with the integral in calculus 2. In calculus 2, there were a lot of integrals that we couldn't compute. We couldn't find the value. For example, here is, look at this integral, 0 to 2 pi. D theta divided by 3 minus sine theta. Well, when it comes to calculus 2, we look at this function and say, oh, look, this is a beautiful function, because sine of theta is always between 1 and -1. So denominator can never be 0. So this is a nice continuous function we are integrating. So the integral should exist, right? So the integral exists. That's all we could say. The integrand, okay, let me put it this way, the integrand is continuous. in the interval 0 to 2 pi always is continuous because denominator is never 0. The only thing that we could say, okay, yeah, this has a number, creates a number. But what is that number? Oh, we couldn't compute. Now, here, I want to use residue theorem to compute this and find a number for it. The process is pretty beautiful and nice because the question is, how do we convert this to a complex integration? Oh, here is how. I'm going to let z, so let z be e to the I theta. When theta goes from 0 to 2 pi, this covers all unit circle, all right? Theta goes from 0 to 2 pi. We get unit circle. Well, instead of going from 0 to 2 pi, I want to go integrate over the unit circle. But in the process, remember, if this is z, then what happens to dz? dz. So note, dz is derivative with respect to theta times d theta. So it is I e to the I theta d theta. But e to the I theta is z itself. So this gives me actually a relationship between d theta and dz. So d theta is dz over iz. Well, that's good enough. But what about sine? That is d theta, right? I'm going to replace d theta by this. How about sine theta? Well, sine theta, if you remember the definition of sine theta, is e to the z, e to the I theta, minus e to the negative I theta, divided by 2i. So sine theta, if I call this one z, right? So this is z, this is 1 over z. So it is sine theta is 1 over 2i. Z minus 1 over z. Well, in this case, I only have sine theta. I could have cosine theta with the same argument. If you have cosine theta, you say, look, cosine theta is e to the I theta plus e to the negative I theta divided by 2, which is 1/2 z plus 1 over z. Okay? Could we could we have an integration instead of just sine t and cosine t, cosine of 2t or sine of 2t? Sure, we could. So if you have cosine of 2t or 2 theta, this is, by definition of cosine, e to the 2I theta plus e to the negative 2I theta, which is 1/2. Oh, we called e to the I theta z, so this is z squared. Plus, this is 1 over z squared. Okay. We could have sine of 3 theta with the same argument, all right? So, but going back to this problem, instead of going from 0 to just in terms of theta, I am going to replace, okay, I am going to write it down to make sure that you see what's going on. So here comes 0 to 2 pi. D theta, 3 minus sine theta. This is the same as integrating over unit circle. We know what d theta is, right? Three minus sine theta. And here is sine theta in terms of z. So 1 over 2i z plus 1 over z so this is 1, 3 minus sine theta, all right? D theta, and d theta is right here. This is d theta. So times d theta, which is dz over iz. Okay, let's multiply this out, okay? If I multiply by z, this will be 3z, here z squared, here 1. And of course, I am going to also multiply by I. So this becomes, sorry. So this becomes integration over the unit circle multiplying by iz. And in numerator, I have dz. So three iz minus this I and this I cancels, minus 1/2. Multiplying by z, you get z squared plus 1. Oh, we can further simplify. I will multiply numerator and denominator by 2 to get rid of this 1/2. So it will be twice integral over the unit circle dz. I can even factor this negative out because uh, I always would love to have the highest degree positive, all right? So it will be z squared. This will be multiplied by 2, so 6 iz. And here, negative 1. This is how this integral, which was from calculus 2, and we know that it converges, it's supposed to give us a number. This is how we convert this to a complex integration, to integration in complex analysis. And now I'm going to compute this and find a number for this. Okay, here is how. So um, I'm going to write it down to emphasize what happened here with that sort of, you can say, change of variable. You can say, well, the integral 0 to 2 pi d theta over 3 minus sine theta. Became the complex integration over the unit circle. Did I have negative 2 outside? I guess I did. So I'm going to put that negative 2 outside. dz. Okay. Well, it was z squared in denominator minus 6i z minus 1. And we can discuss this. We can find a solution for this one by using the residue theorem. Okay. Now, the question is zeros of denominator, which are the simple poles, of course. Which one? Okay, Dell Dawson, you're asking shouldn't be 1 over z. Where do you, which one are you talking about? Let me take you back to here. Are you talking about d theta? In integral when you replace sine theta. Okay, sine theta. Sine theta is right here, the formula for sine theta. And when I replace that, it is 3 minus 1 over 2 iz. You're right, minus 1 over z. Is that what you meant? Yeah, yeah. Oh, you're right. Thank you. Thank you. So it will be, oh, thank you for your attention giving. Okay. And as a result, this will be plus. Okay. And right. So this will be plus 1. And let's go here, plus 1. Okay, good. All right. In order to use the residue theorem, we need zeros of denominator. Okay. Zeros of denominator, let's find out what are those. So we have z squared minus 6iz plus 1 equals 0. Oh, using quadratic equation, all right. So z is negative b plus minus square root of negative b squared, which is a negative 9, minus ac. Okay. So the zeros of denominator are 3i, and here is square root of 10i, so I will factor I. So it is 3 plus minus square root of 10. Okay, good. Thank you, Dale. Thank you, Dale Dawson, for paying attention to that minus. Otherwise, at the end, I would have had a wrong answer. Okay, good. These are the zeros or singularities. Both of them are simple singularities. But look, sorry, 3 plus the square root of 10 is outside. Okay, so 3 plus square root of 10 I is outside. Outside of that contour, outside of that unit circle. But the other one is inside. Yeah, 3 minus the square root of 10. So three minus square root of 10 I is inside. It's important to know which one is inside, which one is outside. There are only 2 of them. So that means the value of this integral is going to be 2 pi I residue at this singularity that is inside, okay? So I need to find the residue of this integral, this integrand, this function. at this point. It's a simple pole, so I will just use, for example, 2b. So residue of the function at, let's call this one z naught, which is inside. And that's what I care about. Is using 2b, so numerator divided by derivative of denominator. 2z minus 6i evaluated for z naught. Sorry. Okay. Oh, this is z naught. So let's replace z by this number, see what we get. So this is going to be 1 twice this, which is 6i minus 2 square root of 10i, and then we have negative 6i. So 6i's cancel. So this is just negative this guy. Note that is the residue. So the integral, this I'm talking about this integral now. This -2 is a constant, that's fine. It will be 2 pi I times that residue. So here we go. So 0 to 2 pi d theta over 3 minus sine theta is that -2 and another 2 pi is a -4 pi I times this number, which is the residue. Sorry, again. So negative, positive, I cancels. So it will be 4 pi. Oh, one of 2's cancels as well. So it will be pi over the square root of. Okay. Can you believe this? We found value for this one. We found a value for this very interesting integral. We only knew that the integral makes sense, but what was its value? We didn't know. Okay, now we found a value for it. This actually is this much. Right? That is beauty of residue theorem. wouldn't it be 2 pi? Let's see. Yeah, I had here. It was 2 pi and another negative 2 in the view. I mean, outside of the integral. So that is why it became negative 4 pi. Okay? That I included that negative 2. That's why we get negative 4 pi I. Any question? Isn't that nice? I am going to give you more of this, but you need to practice and enjoy this just this application that I talked about. Oh, please, this is section 16.4. Go ahead and practice this on page, my book says 133. Let's see, maybe one more time. I'll look at page number. Oh, 733, not 133. Gosh. Page 733. Oh, that's my book. Your book might say something else. Problems number 1 to 9, you can just work on those. And if you have any question, please ask me next time. See, I don't get a lot of questions from you guys. Ask me question. If you have hard time understanding a topic or have difficulty doing some of the problems, oh, please let me know. Of course, uh, I am sure the difficulty that you have, other students also have that difficulty, and they will appreciate if you you ask. That they are shy, they don't ask. Um, sure, we can do that. We can talk about Laurent series uh, as well. All right, all right. So, uh, if you don't have any question, comment, then I will see you on Thursday. Have a good day, everybody. Bye bye now. Thank you, Delson.